All right, good morning, everyone. Today we're going to finish Gauss's Law, and I've posted your homework for chapter 24. You'll turn that in on Friday when we take the midterm, which will be 24, and then 26, 27, and 28. So let me review, first of all, just some of the concepts we discussed last day. So you remember we talked about symmetry. And symmetry was this idea that if you have a charge distribution which is highly symmetric, meaning it looks the same when you perform some changes, we said the electric field would have to mirror the symmetry of the charge distribution. This was the concept of symmetry. And then we introduced the concept of electric flux, right? Electric flux being a measure of the degree to which electric field lines penetrate through some kind of a surface. And we had surfaces which were closed surfaces, like a sphere would be closed, right? And then you also have open surfaces. An open surface is one that has two different sides, or you can go from one side to the other without penetrating through the surface. So you can calculate the flux through a particular surface. So we're going to talk about Gauss's law today, or tie these concepts together to talk about Gauss's law and do some practical calculations. But just as a warm-up exercise, if you could take out your voting cards. So let's imagine that I have, we talked about something last class called planar symmetry. So there's a large plane or sheet of charge. Now imagine I have a large plane of charge as shown on the screen, and I want you to calculate the total amount of electric flux through a cube, and the side length of the cube are 1 by 1 by 1, 1 meter by 1 meter by 1 meter. So that cube is centered on the plane. So I want you to calculate the total amount of electric flux through that cube. So I'll give you a short amount of time to think individually here, and then in a moment I'll ask you to show your vote. Okay, does anyone need more time? So, a little bit more time. All right, on the count of 3, let's show our vote. How much flux is there through that cube? 3, 2, 1. All right, take a moment to try to convince your neighbor. There seems to be a bit of a smattering of different answers here. So try to convince your neighbor which one's the correct thing. All right, so let's take another vote here. On the count of 3, 2, 1. Right, we seem to have converged to C. About 85% or so C. So that is correct. 2 Newton meter squared per coulomb, which would be the units of electric flux, right? Electric field just being newtons per coulomb and an area being meters squared. So that's how much flux is through the box. It's a positive flux because field lines are leaving the box. So inside the box, there's a source of field lines, and there's a net amount of field lines that are leaving. This is a two-dimensional cross-section of that box. Yes?
So the direction of the lines does not, like the direction of the field lines does not play a part in it? Because some of them are pointing, some of them would have like a negative y component and a positive y component.
Right. Okay, so on the top surface of the box, this is a good question. The electric field line is pointing the same direction as the area vector, so that gives you a positive flux. On the bottom side of the box, the electric field vectors also point in the same direction as the area vector, which is outwards. So you also get a positive flux. So you get 1 on this side, Newton meter squared per coulomb, and 1 up here. You get none on any of the other 1, 2, 3, 4 faces, only on the top and bottom face. The side faces don't have any flux through them because the field, due to the plane of charge, since we're dealing with planar symmetry, we could argue the field has to point perpendicularly away from the plane. And in fact, we already know that. We already know the electric field due to a plane. It points perpendicularly away from the plane. Yes?
So is the area vector in 2 dimensions?
The area vector is a vector in 3 space, right? It could point in any direction. So for example, on the top, this is the two-dimensional cross-section. On the top of the box, the area vector points up. Right? On the side of the box, the area vector points this way. And this whole face would have a constant area vector. Right? Every little piece of the area points in that direction. If it was curved, the area vector would change, like a sphere, for example. And then on the face, if there's a face that's pointing this way, the area vector would point this way. So in fact, the area vector just depends on what face you're on of the surface. Since they're flat surfaces, they just point in a constant direction on any side of the surface itself. All right, so last day we looked at, we wrote down the flux. Phi sub e through a surface is the double integral of E dot dA. Right, and then we put a circle here, and that circle indicated is just a special kind of surface, and it's a surface that is closed. So let's look at the flux through some particular closed surfaces. Let's look at positive charge, and then a closed surface, which I'll just call a Gaussian surface. So a Gaussian surface is something, we're just going to create these imaginary surfaces, which we call Gaussian surfaces, and we're going to calculate the flux through these surfaces. So this is a Gaussian surface, Gaussian surface G, say. All right, now let's think about the flux through this surface. Is the flux through this surface positive, negative, or 0? So give you a moment to prepare your vote. How much flux is through this sphere? Okay. 3, let's take a moment to vote here. 3, 2, 1. All right, C is correct. There's 0 flux. Right, because if I was to draw the electric field due to the positive charge, I just drew 4 lines here. Now, yeah, none of these lines actually create any flux on the surface. But this one, as it enters here, is negative flux. enters and as it exits, it's positive flux, and those two contributions cancel each other. Now it's true that if I actually sketch some more lines in here, right, because the field line diagram is just a representation of the field, it's true that there are more lines puncturing through the near side of the surface, right, that are closer to the charge because they're more tightly, the lines are closer together, but the area is also smaller on this side that's closer to the charge. They're more spread out over here, so it's a bigger area, the field is weaker. If you mathematically did the calculation, this integral, you would find it would have to equal 0, but physically we can make the argument that whatever comes in has to equal what goes out, since there's nowhere for it to begin or end unless you have a positive or negative charge. Is there a question? All right, so let's look at one more example here. Well, let's look at a couple more examples. Let's take the same Gaussian surface, but I'm going to move the positive charge and put it inside. Okay. And is the total flux positive, negative, or 0, 3, 2, 1? All right, it isn't correct. It is positive, right? Because the area vector for the sphere always points radially outwards, and the electric field is always pointing radially outwards as well, so you have a positive flux. Now, let's change this question slightly, and I'm going to erase these field lines here, and let's say I add a negative charge right there. I'll give you a moment to think about this. How does the total amount of flux change if I kind of make it like a little dipole here? Plus charge and a negative charge. And we'll make them equal magnitude, just opposite sign. How does the flux change here? Is there a question?
No, how you were asking.
Okay, yeah, so let's, give you a moment to think about this, and then we'll take a vote. If something does change, you want to think about what changes and why. Okay, so 3, 2, 1.
Yeah, which one is
Positive, negative, or 0?
Change or absolute?
What's that?
what's the change? Is it positive change?
Oh. So basically, I'm just asking, what's the flux here? Is it positive, negative, or 0?
Oh, it's a percentage.
Yeah. So same question, but now there's just another. Yeah. Thanks for the clarification there. Same question, but I just add a negative charge in here. What's the flux? Positive, negative, or 0? All right. So it is positive, correct? Right. Now, take 30 seconds. Explain to your neighbor what changes, though. What changes compared to the case where we had no negative charge?
Stronger on that one side.
All right, so what changes here? What's different? And what's the same versus, when the negative charge is there and when the negative charge isn't there? Thoughts here? Yes?
The flux on the side of the circle is closest to the negative charge gets stronger, while the flux on the other side of the circle is smaller.
Okay, so because we have a dipole, the field lines kind of bend now, right? they're more tightly packed when you're in between the dipole, and they're less dense kind of on the other side, right? So here's a higher density of lines, meaning the flux is still positive, right? But now more of those lines are kind of bent over to this side, and less of them are over here. Now, is the flux, so it's still positive, right? But is it more or less than what it was before? Yeah.
I would argue that it's less than before because now the area vector is not going to be aligned with the electric field vector. They're going to be a little bit of an offset due to the curvature, and that would decrease it.
Okay. So there's some angle now between, there could potentially be some angle between the electric field vector and the area vector, which could, it doesn't make the calculation quite so simple. Okay? Yes.
I think it's going to be the same. I think that's going to happen, but I think that it's not going to affect the value. So I think that's just going to be like a redistribution of the lines. Then also you have the factor that because there's a negative charge, that field between the positive and negative is probably a little bit stronger than just the positive pushing out. So, like
Okay. All right, so let's just do the calculation. First of all, let's just say I'm going to draw a sphere. Here's my Gaussian sphere. And your Gaussian surface, it's just an imaginary surface. It can be any shape, right? That sphere is the most symmetric shape, right? It has the most degrees of symmetry. And I'm going to put a positive charge, Q, right in the center of that sphere. And I'm going to say that this sphere has radius capital R. Okay, so let's calculate the flux through this sphere. The electric flux through the sphere is equal to the double integral of E dot dA, and it's a closed surface. Okay, so everywhere on the surface of the sphere, the electric field vector points radially away, right? And it has a value of 1 over 4 pi epsilon naught Q over R squared, and R hat. Electric field is a vector, it points radially outwards. So let's plug that into the equation. So I get the double integral over the closed surface of Q, over 1 over 4 pi epsilon naught. I have a Q, and then I have a 1 over R squared, and then I have an R hat. And then I'm dotting that into, that's my E. Right? And what I'm doing is I'm dotting that into the area vector. And this little patch of area right here has an area vector, so the dA vector is just going to equal whatever its magnitude is multiplied by R hat. For a sphere, it's always R hat. Right? The sphere area vector, the vector that is normal to a spherical surface is radial. Okay, so I dot this into R hat dA. Okay, now let's just do a little bit of vector algebra here. And R hat dot R hat, it's kind of similar to I hat dot I hat. I have two unit vectors that point in the same direction. What does that have to give you? One, right? Because there's no angle in between. So R hat dot R hat has to equal 1. Cosine of 0 is 1. So what I can do then is, well, let's simplify this a little bit more. On the surface of the sphere, this R is always capital R because it's just the radius, right? Now everything here is constant, so I can take it outside the integral. So I get Q over 4 pi epsilon naught R squared. And then I have the integral over the closed surface dA. Okay, now I'm not going to set up this integral or parameterize the sphere, but this is something we could do in spherical coordinates. For example, we could integrate R squared sine theta d theta d phi, right? That would be the area element in spherical coordinates. Anyone familiar? You guys familiar with spherical coordinates from calculus? All right. But what is the surface area of a sphere? 4 pi r squared, exactly, right? So let's just, this equals 4 pi r squared, right? So something interesting happens. The 4 pi r squared cancels with the 4 pi r squared, and I just get q over epsilon naught. So the flux through the sphere only depends q on how much charge is inside divided by epsilon naught, the permittivity of free space. Now let's try to generalize this result a little bit by saying that, let's say I distort, because the question could be asked, all right, well that's cool for a sphere, but does it work for any shape? And the answer is, it does, because imagine I take this sphere and I take some pi slices of this sphere, and I say, all right, well, you know, I want to make it a little bit smaller there, and then over here I want to take a bigger pi slice, right? But I want it to be larger here, right? And I could do that iteratively as many times as I would like, and what I would get, it would break this integral into a number of different pieces, but each piece would give you a proportional same amount of flux, right? And you'd always get q over epsilon naught. So basically, this result works for any. It's independent of shape of the surface. Independent of surface, shape. So that's one point to recognize, is that the flux is independent of the surface shape. And secondly, what happens if, you know, let's say I have more than one charge inside. I have multiple charges. You know, not just one. Let's say I have another one here. You know, let's say I have one here. And let's say over here I have some, you know, body of charge. Well, since the electric field, we already know that the electric field obeys the superposition principle. So if we wanted to calculate the flux through a surface of arbitrary shape with multiple charges, we would just have to calculate the flux due to each individual charge, add them all up to get the total flux, and this same argument would go through. So what we would find when we put this all together is we arrive at Gauss's law, right? The name of the chapter, Gauss's law, which says the flux through any closed surface, and this is a very general result, which is a property of electric fields, tells us something very interesting about electric fields. The flux through any closed surface is equal to the enclosed charge divided by epsilon naught. So this is valid for any closed surface. And in fact, this law right here is more general. This law right here is more general than Coulomb's law. More general than Coulomb's law. Although historically, it's part of what we call Maxwell's equations. One of 4 Maxwell's equations, though historically it was discovered afterwards. The reason it's more general is because it also works not just for static charges, but for moving charge distributions as well. Right? Now, what are we going to use Gauss's law for? Well, what we're going to use Gauss's law for is we're going to use this to, for our purposes here, we're going to use it to find E field of charge distributions. Okay, you might say, well, I already know how to find the electric field due to charge distribution. We already spent a whole chapter on that, right? Right where we wrote those integrals. Now, to add up all the little pieces together, and that's true, but Coulomb's law will give us another way to utilize the principles of symmetry, or sorry, Gauss's law, utilizing the principles of symmetry to calculate the electric field in charge configurations that are more complicated than we would have been able to with just setting up integrals. Now you could do it with integrals, it's just the integrals are more complicated. This just kind of gives us an easier way to learn interesting things in a more simple way. Question?
So how does this relate to what we were talking about with symmetry? Like what if the shape does not match the symmetry of the electric field?
Okay, excellent question, and we're going to come to that in a moment here. Okay? All right, so yeah, excellent question. Now, so let's look at this, and just to show you kind of what this looks like. Well, let's try an example here. So, okay, so here I have different shapes. Okay, one of them is a square, one of them, and then the others are circles with different radius. This one's a bigger charge. So I want you to determine through which surface is the flux the greatest. Which of those surfaces gives you the greatest amount of flux? I'll give you a moment to prepare your vote. E is all over now. All right, so the count of three. Well, maybe you want to team. Well, you can team up with your neighbor if you want.
Yeah.
Yeah, that's creative. I like that. All right, so. All right, many of you have got it correct. Which ones have the most flux? Well, based on what we just learned, the ones that have the most charge in it. Right, so B and E have the greatest amount of flux. They're that weird. Where it doesn't matter the fact that this one has a smaller area, right? Because now physically what's happening, it has a smaller area, so the lines are more compact. Right? So the field is stronger if you're a smaller area, but those field lines have to go somewhere. They still have to exit the surface, so you have a bigger area here, but it all still has to exit that way. It's kind of like if you had a speaker, right? If you were to calculate the total amount of energy that's transmitted from the speaker with a small little sphere, right? There's a certain amount of energy. Now, when you're farther out, that's just spread out over a larger area, but it's still the same total amount of energy. So think about the sun, right? There's a certain amount of solar radiant output that's being, imagine a sphere that is the distance, that has the radius from the sun to the earth, right? That's the total radiant solar output of the sun. Now the earth is just a tiny speck on that entire sphere, right? But that's where we get our energy from, right? So it's a similar way. All that energy has to go somewhere. Now, this is not energy that's flowing, right? But it's field lines. They have to go somewhere. They start on positive charge and they end on negative charge. All right, now which one is going to be the least? All the others are actually the same and they're equal, right? Even though this one is a square and this is a larger circle, the flux, Gauss's law says the flux, the whole idea of Gauss's law is this can be hard to calculate, the left-hand side of the equation, but the right-hand side is easy. It's just Q over epsilon naught. Now I wrote Q in over epsilon naught. So what I mean by that is Q enclosed, the total amount of enclosed charge inside that surface, the total amount of charge that's inside the surface. So this flux integral is hard, right? But the beauty of Gauss's law is it says that through any closed surface, it always equals Q enclosed over epsilon naught. So if I was to calculate it through You know, I did the calculation for a sphere in just 1 point charge. That's pretty simple. It'd be kind of hard, and I actually give you a homework problem related to this, right? But you have to set up an integral to do it through a more complicated surface because the field isn't constant over that surface, right? But it still can be done, but we know it's the same in this case via Gauss's law. Yes?
When you were doing that thing where you're changing the radius of certain parts of the circle, could you do that with the square and just look at it as a circle with each point having a different radius?
Yeah, I mean, you could think of it as
Is that
every little chunk is approximately the arc length subtended from a center point. And you could construct a square by several different,
in spherical coordinates?
well, yeah, I mean, you could, right? There's several different arc lengths that are all, and these are called solid angles that are subtended from a common point. So it'd be like integrably, you're adding up a bunch of different radiuses, and you make it look like a square. That's why Gauss's law is true, right? That's the mathematics underneath it, or some of the mathematics underneath it. Good question, yes. All right, so let's say then that I have a box now, okay? And just by looking at that box, each of those arrows has the same magnitude, represents electric field. How much charge or charges are inside that box? F is the white side. These are 3, 2, 1. Okay, take a moment, explain to your neighbor which one has to be correct.
That would take another
All right, 3. Let's take a vote here. Okay, so 3, 2, 1. Yeah, E is in fact, you guys got it here, a net negative charge. Can someone explain why it's a net negative charge inside? Yeah.
Because if all those are the same magnitude, there's 4 going in and only 2 going out. So that means you have a net of 2 arrows worth going in, and if it's going inward, it's net negative.
So those field lines are going in, they have to end somewhere, and they end on the negative charge. If they end on the negative charge, they're not escaping because the negative charge is a sink of field lines. Once they fall into the sink, they don't escape the sink. All right, good. All right, now let's look at a, more of a complicated charge distribution. This is a box or a cube of charge, a cube of positive charge. So let's say we want to, and we're going to do an example of this in a moment, but just as a warm-up exercise here, let's say we want to calculate the electric field of this cube. Using the principles of symmetry along with Gauss's law, what kind of shape would you want to use in order to determine the electric field due to this box? What kind of Gaussian, because your Gaussian surface can be any shape, or what kind of shape would you want to choose that would allow you to calculate the electric field due to the box? A moment to think about this. Okay, let's get ready to prepare our votes. And 3, 2, 1. Okay, so I want you to explain this one to your neighbor. What shape would allow us to calculate the electric field of this box? All right, and let's take a vote here. Here, prepare your votes. 3, 2, 1. We got about 40% A's, 40% C's, about 10% C, or sorry, 40% C's, 40% A's, and then 10% B's, 10% D's. So D is correct. Neither A nor B will allow us to find the electric field. So can someone explain who chose D, why that was correct? I saw a couple D's over on this side of the class. Yes?
I thought it was because it didn't specify how big or small the sphere was, because if the sphere completely surrounded the cube, then you'd be able to tell, but if the sphere was within the cube, then it wouldn't tell you anything about it.
Well, actually, in either cases, it wouldn't work.
Oh, then I'm
Yeah. Yes?
I'm pretty sure the symmetry of the distribution of charges doesn't match the symmetry of the Gaussian surface, because the electric field leaving the cube wouldn't be uniform. More charges would kind of bunch up near the corners, and because it's not a uniform field, it wouldn't be like symmetric in certain like movements. So it wouldn't match the symmetry of just a Gaussian cube surrounding.
Okay, so there's something to do with symmetry here. Very good. Yes?
I don't think you would use Gauss's law to calculate the electric field. You would use it to calculate the flux.
Well, all right. So in fact, you couldn't use it in either case because imagine, let's say you put a big cube around this slow cube, right? Well, what use would Gauss's law really be for you in this case? Because if you had Gauss's law, right, and you tried to, let's say, had a big cube that was surrounding it, the electric field due to this cube is kind of complicated, right? Because it's not like a sphere. It's not like a sphere of charge where the electric field is always radial, right? Because at the edges, it kind of bends a little bit more, right? So it's not always pointing, you know, it would be a complicated integral to do over the sphere. So that would be very complicated to do. And sure, this equals this, right? But it doesn't tell us anything. There's the sphere, I would put it this way, the cube doesn't have a high degree of symmetry. It has what we call discrete symmetry, right? Meaning that if only for certain axes, if you rotate it by, say, 90 degrees, it looks the same. But it's much less symmetric than a sphere, for example, right? You can choose, for a sphere, you can choose any axis through the center, rotate it only a little bit, and it looks exactly the same. So the sphere is much, much more highly symmetric. So the point of this question here is Gauss's law wouldn't help us calculate the electric field. If you wanted to calculate the electric field, you really have to just go back to chapter 23, use Coulomb's law, set up the integral, and it would be a real mess. Yes, question?
I lost my question.
All right, so let's look at a sphere, right? Now, let's actually do this calculation for a sphere, okay? Use Gauss's law to find the electric field due to an insulating sphere. And I'm going to make the sphere insulating because I want it to be like a big styrofoam ball of charge, where charge is on the inside and it's on the outside. It's not a conductor where it's on the outside, right? It occupies the whole sphere. So insulating, charged sphere. This is application of Gauss's law. So here's my sphere. And I'm going to say, okay, this sphere is uniformly charged. Uniform. Doesn't have to be necessarily uniformly charged, but its charge distribution has to be radially symmetric. Okay, so let's say that there's this sphere has radius capital R and charge capital Q, and the question is find E. inside and out. Right now, you might remember that we made an argument earlier in the course that outside this sphere, the electric field has to just look like that, what it is for a point charge. Okay? But I didn't really prove that, and also too, in that I didn't solve the integral for you. It's a complicated integral to add up all those disks of different radii, right? But I also didn't say anything about the electric field inside the sphere, the insulating sphere, because that would also be a mess. But now we can use Gauss's law to find it in a very easy way. So let's do that. Let's first of all look inside. So I'm going to look at an R less than capital R, or in other words, inside. Inside the sphere. So since my ball of charge there is radially symmetric, I want to choose a Gaussian surface which matches the symmetry of the charge distribution. So I'm going to choose a sphere as my Gaussian surface G. Right, and I'm going to put that Gaussian surface in the region of where I want to find the electric field, that is inside the distribution of charge. Right, I wouldn't want to put a box inside because that would just make the calculation really, really hard. I want to choose a Gaussian sphere, flux through the Gaussian surface that resembles the symmetry of the charge distribution. So I choose a sphere here. Okay. All right, now, in order to do that, I basically just have to calculate the left-hand side of the equation and the right-hand side of the equation, and then solve for E. That's basically what we're going to do here. That's the whole idea, which is going to allow us to solve the problem. Now, just to write this in its most general form, let's say we're completely ignorant about electric field. We don't know anything about the electric field. We could say, all right, well, in general, in spherical coordinates, the electric field, it could have a radial component, right? And that radial component could depend on r theta phi in the r hat. It could have a theta component, which could depend on r theta phi in the theta hat. And it could have a phi component in the r theta phi hat. That's kind of complicated, right? But in polar coordinates, there could be 3 different components to your electric field. Now we can make here's where it gets simple. If we make an argument using radial symmetry, right? Any rotation about any axis through the center leaves the charge distribution invariant, which basically means it can't depend on, there can't be a phi hat component, there can't be a theta hat component, and it can't depend on theta and phi. So this is where symmetry comes in. Just by symmetry alone, we know our electric field has to be radial, and it can only depend on r. Right? That's because of these rotations. It has to lead. It has to give you a field that doesn't depend on if the sphere rotates or not, because it looks the same. Right? So if I add pi to theta, those are, and you don't have to really worry about spherical coordinates in this class. You don't have to worry about that. But that's just basically how symmetry ties in here. Okay? So then what we say is, let's use Gauss's law and say, okay, so the electric field, the flux through the electric field is, here, let's just grab some paper. Just so no one, yeah, no problem, just so no one slips, because it's, yeah, that's fine. Just because water is slippery, you know? That's actually an interesting question, why water is slippery. You know, if you step on ice, why is it slippery? Sorry. No problem.
Don't worry about it.
What's up?
All right, so and if you need more, just grab some. But yeah, it's not a problem. All right, so let's just calculate the flux here. Okay, so this is E dot dA, and we know that this has to equal the integral of E. Now we know that E can only be a function of R, and our dA vector looks like this. Okay, now here's where we can make some arguments about the sphere itself. Since the electric field is constant over the surface of the sphere, right? Because it's just a sphere, it has the same R everywhere, we can take it outside of the integral and we can write E sub R as a function of R equals the integral of dA, right? So this is just E sub R as a function of R is 4 pi little r squared. So we've just figured out the left-hand side of the equation. And now what we want to do is we want to use Gauss's law to figure out the right-hand side of the equation. And the right-hand side of the equation is just the total charge inside divided by epsilon naught. So total charge inside, so this has to equal, this is by Gauss's law, this has to equal, well, Q inside over epsilon naught. Now how much charge is inside? Not Q, right, a portion of Q. So how do we figure out how much charge is inside? Well, we'll use the volume, charge, density, rho. That's the total amount of coulombs per cubic meter, rho. Rho is just equal to Q over 4/3 pi capital R cubed. So the amount of charge that's inside this sphere is going to be the charge per unit volume, which is rho, times the volume, which is 4/3 pi little r cubed, and then all divided by epsilon naught. So this term up here, that is the amount of enclosed charge. Charge per unit volume times the volume. Right? So when we multiply that out, what we get is the 4/3 pi cancels, and we get Q over epsilon naught, little r cubed over big R cubed. Okay, and this equals 4 pi r squared E of R. So combining, what we get is if we solve for E sub R as a function of R, E sub R as a function of R is just going to equal Q over 4 pi epsilon naught, R over R cubed. So nothing, so now, so I went through this rather quickly here, right? But you'll want to familiarize yourself with all the steps, because all the steps will be familiar with any Gauss's law kinds of problems, right? Now, if we think about it here, in a few lines, I found the electric field inside the sphere, which would have otherwise been very difficult to do using an integral, right? Using Coulomb's law. But Gauss's law gave us a way to do it in, a couple steps. So we've greatly simplified the ability to solve or find the electric field in charge distributions which are highly symmetric. Okay, so then let's plot this. Let's plot the electric field as a function of R, and here's the radius of the sphere. So what this equation says is when you're at the very center, little r is 0, there's no electric field. Right? But the electric field grows linearly as you move outward, so it goes like this. And that kind of makes sense. As you move to one side, you're closer towards this part of the charge than you are from this. So there should be a field that's growing stronger and stronger as you go out. Now, when you're outside, when you're outside the sphere, or little r is bigger than big R, you're going to get from Gauss's law exactly what you would expect, that which is just due to the point charge. So you'd get the 1 over little r squared when you're outside the sphere. So essentially, we do exactly the same argument as I did over here. The only thing that would really change is instead of putting this mess right here, where I circled it, you just put a capital Q. Right? If I did everything the same, and I put a capital Q here, and I made my Gaussian surface outside, so it encloses everything, then everything goes to the same. That just turns into a capital Q, and then I get this as my result. And I found the electric field due to a sphere. All right, which otherwise would have been rather complicated to find. Now, just one point, and then we'll do a few things next class, but we're pretty much done this chapter at this point. I'll say a few more things beginning of next class, but let's imagine, so we talked about planar symmetry, spherical symmetry, cylindrical symmetry. So this is really spherical symmetry, right? What other things could I do for a sphere? I could have nested spheres, right? And again, you would use a spherical Gaussian surface, but you could find the electric field due to nested spheres, because it's spherically symmetric. And your Gaussian surface would want to be a sphere. If I had a charge distribution which was cylindrically symmetric, you'd want your Gaussian surface to be a cylinder, right? If I had and then in the next class, what we'll look at is a charge distribution which has planar symmetry, and we'll use that to find the electric field. Okay? So those are the basic symmetries which allow us to find the electric field. So just a few things to say about this next class, but that's most of this chapter, and we will start actually on chapter 29 on Wednesday as well. That won't be on the midterm though. Yeah, you'll have a quiz this week up to kind of today's material. Chapter 26, 27, 28, and 24. See you. Yes. Where? This, because it's a constant, it comes outside of the integral. It has to be constant over the surface of the sphere.
Yeah, I don't think I can.
And the reason it has to be constant is because you couldn't depend on anything else. Well, because every point, no matter where you are, you're the same distance away. You can rotate things and it looks the same. So it comes outside the integral. And when I integrate, this is over the closed surface, out of all those little tiles, I just get the area of that Gaussian sphere, which is 4 pi little r squared. Yeah, thank you.
I just wanted to think, like,
sure.
How did you get, like,
oh, so 2 of these r's cancel with 2 of those, leaving just 1.
Oh.
Yeah.
To where our campus has